Hi, welcome to this second or third episode on compilation. In the last episode, we saw that compilation is a very complicated and theoretical process which consists of having a written program written in a manner where human can read it and transform that. I would like to say it's a poem into a program, and a machine program, uh, like any other program you ever know, like YouTube you are watching on right now. So that process of creating programs is called compilation. And the general idea of compilation, as we saw in the last episode, is having a file or a bunch of files. We name them source code, and taking that those files or that file and turning them into a functioning program that could be executed on any machine or on a certain machine specifically. So we saw that that process is called compilation, and generally that process is subdivided in 6 steps. The first step is the source code. This is the easiest if you know a little bit about programming step, because this is just your code you have just written. So it's your main.c file. It's your, for example, add.h, your header file. So it's the human readable code. So that's the first step. So in order to illustrate this, I'm going to compile, we're going to work with a certain program. So if I list files that are on in this directory right now, you see that I have 2 files. I have a header file and a main.c file. Those are my source code. I want to make a program out of those. So let's take a look what is in the header file, for example. So we run, for example, vim header, and we see that in the vim header file, we have a declaration of a function called add. That is a simple function. It's just going to take 2 numbers and add them. We haven't written the implementation yet of that function. We have just declared the function itself. I have done this to show the idea that compiling, you compiling isn't necessary a process that is executed or is done only on a single file, but it could be done on multiple, even hundreds of files. Nothing interesting in this file. So let's, for example, look at what is the contents of the main, the other file. There is nothing in here. So this is where we are going to write the implementation of our add function. So it's a simple C program. It's going to be simple. So for a C program, we start by doing something that you could notice that we just included the systems file, the system file that contains it's a library, it's a header file, obviously, that contains the ins and outputs of our program. So it's you can think of it's a header file that contains the functions like printfs, things that function that works with the inputs and the outputs. We already have that, but we could even use another header file that doesn't come with the C language we just created. So we could include, for example, our header file, for example. Okay, so let's write the implementation of our function. So let's declare, as remember, our function returns an integer. So the result, for example, is going to be an integer. So we call add and we pass it 68 and 1, for example. And we we could obviously return to say that the program has executed and finished successfully. But we want, for example, to see our result in the output. So one output could be the console, for example. The output could be anything really, anything that you can support the streamline of data. But for now, it's going to be our terminal or our console terminal. So we're going to use a function called printf because we are going to be able to use this kind of function because we have included this header file. Printf is defined in the stdio header file, and the add function here is included into our header file. So for the so this is fine, but you can notice that even though we can suppose that our function add is going to add numbers, we haven't written the implementation of that function yet. But obviously, we could write the implementation of it in this file. So let's, for example, save this file and write the implementation of our function. So we have this function right here. So the implementation of this function is going to be easy because we all know how to add, right? So so you take so you take two parameters and you return their sum. That's what it does. So this is our small program, insignificant, obviously, but it's easy enough to uh, illustrate what I want to show. So I just written the implementation of add. So if I'm not wrong, I think the our program is done. So yes, yes. So for example, we can now try to compile it without. So we can now try to make all of to compile. So which means to make all of to go through all of these steps. So one way to do that is to first let's see if the compiler, we have seen that compilation obviously is done by a program that is called a compiler. And for C, and because our program is written in C, the compiler for the C language is called GCC. There are obviously other compilers. You can even write your own if you are courageous enough. But let's see the most widely used compiler for C programs if it's installed on our machine. We can see that it's installed on this machine. So let's use it. So one way to compile our program is to call the program, hand it all the files as stated on the first step. You hand it all the files that your program uses, which is the implementation of our main. I made a little bit of an error. It's called header. And stating that the name of the executable. So for example, this little minus and O, it means that we want to stop the the compilation at step 6 where we produce an executable, right? We want an executable because that's an executable, it's in its name. That's what we're going to use to execute, like to run the program. So the name of our executable, because we are on Windows, I'm going to name, even if we are using Linux, I'm going to name it main.exe. Let's hit enter. We can notice that the compilation is done. By looking into our project folder, we notice that there is a new file called main.exe, which is our executable. Let's look at the type of our file, the nature for this file. So we notice that it's an executable. It's an executable that can be run on any on a 8664 processor architecture. We can see that it's dependent on certain libraries like lib64. We can see that it's dynamically linked, which we'll come to later because we can see that there is probably a correlation between linking and dynamically linking. Here we can see again that it's an executable. Yeah, you can notice it's an executable. So let's try to run it to see if it works. So remember, our program, what it does is it should add two numbers that we have hard coded in, which are 68 and 1. So if you know how to add, normally you should uh, uh, know the result of this program if I hit enter. 69. So our program, our little insignificant program, just worked. So how did it do it? How did the GCC, the compiler, did all of this to produce the final result, which is 69? It did the compilation process. That's what it did. So let's go to the next step, which is because we have just done the first step, which is writing the code, writing the necessary code for our program to run. The, the thing is, when you run commands like this, we can see that we produced we stopped we stopped the compilation at step 6, which is the last step to produce an executable. But what if we need, for example, the assembly code? Maybe we need the pre-processing code. There is a way to do that. There is a way of obtaining files. So the thing to have in mind is that each step in the compilation process, it produces a file, or even it produces files. The first step is your source code. We just did it. And let's go to the second step, which is named the pre-processing. So the preprocessing handles lines that start with the ladder. So if I show you again, so the preprocessing handles lines that start with this ladder kind of symbol. For example, uh, this. So what it's going to do is going to replace every line that starts with this symbol with the actual code from the included file. So in our case, when we do include header.h, we are including the declaration of and the implementation of our function add. When we write include stdio.h, we are going to add every piece of code that is necessary that is written in this header file, which is the implementation and the declaration of those functions, like for example printf. So these lines are going to be replaced by their respective code. So it produces a file, and that file, we can name that file. So we could say that in order to start the preprocessing, we have the main.c, we produce like the main.i. So let's see how it works. So let's exit Vim here. So let's see that it in action, it will be nice. So for example, we do GCC. Um, we do like this, and we pass in all our all our files that makes up our program, and we do like that, and we hit enter. Okay, there's a little bit of an issue. Um, Maybe we could use we're not could we could use the compile for C++, which is called G++. Let's look again in our folder. We notice that we will produce a file. Let's look at that file, its nature. Let's look at the nature of that file. We notice that it's a source code, it's a C source code, and it's ASCII text, which means that it's like this one. It's a file with characters, readable, human readable characters. So let's view it. Okay, you can see what is like you can read it. It's code, obviously it's source code, but you can still read it. It's human readable. You can see that we included a bunch of files, a bunch of libraries like stdio, and we included, for example, other libraries that are very libc. We've included libc. So we have included also other bunch of. This is stdio we have included. We can see that it's our file, but with a lot of files. So let's try to go and see if we could reach our code. Normally, we should reach our code. Maybe it's down. Okay, so this is it. You can see this is our program. This is our initial program. You can see that where we wrote header, it has been replaced by the declaration and the implementation of our function. So the preprocessing stage it consists of taking all those files that are that program divided in multiple files, putting it in the same file. That's what step number 2 consists of. Taking a bunch of files, putting them together in one big file. So that's the second step, preprocessing. The third step is called compilation. Even though it's called compilation, it's not the, you would think that because it's named compilation, it's the last step of the process, but it's not. So the compiler in this we have used the compiler, we have used GCC, and we have even used G++ for C++, but it's the same really. It's the same, but C++ handles classes and things like that. Um, let's so the compiler translates preprocessed C program or C code into assembly language. That's important because now we know from the last episode what is assembly. Assembly is a low level code that is readable but at a certain limit. So in the compilation stage, we transform the main.i file, which contains the whole functions, the correlations and functions and our programs together, and we transform all of that into assembly language. So assembly language, as we saw, it's still human readable, but at a certain limit, as I said. So at this step, the compiler does what is known as syntax checking and convert the C program or the C++ code into assembly code. So on this step, the main.i file enters into this step, and this step produces main.s file. So obviously you can start seeing the a little bit of a pattern, right? So these files are fed into the pre-processing stage. The pre-processing stage produces a file main.i. This main.i file is fed into the third step of the compilation process, and the third step of the compilation process produces the file that is called main.s. So you have this kind of snake thing going on, where a file is produced and fed into the next step, and which that step produces a file which is fed into the next step. So let's look at it. Let's see how the compilation is done. So in order to do compilation, uh, and let's because we have the file that has been produced by the pre-processing stage, we could use it directly instead of using the source where we have the where we have multiple files, which we even get an error if we use the multiple files, but we're going to take the advantage that we have a file where everything is together to use it on the third step. So we start the compilation at S. So we run it, no errors, we look into it, we see that again, a file has been produced called main.s. So let's take a look again what is in main.s. Mm, as we expected, we could we could see that this is assembly language, right? It has a bunch of things. It does more than what our program does, because our program, what it does, it just takes two numbers and adds them. But there are a lot of things that go on in the background that are needed in order to make your program possible. So that's why our code, our assembly code, is a little bit more. So we could try to see where our program actually is written in assembly language. For example, we could try to find the number 68 in our program. You could see here, right? We could see that this instruction means that we are moving a certain number in a register. So we are moving 68 in a register named like this, and we are moving 1 in a register named like that. And we should now notice where we are calling the add instruction in. Where do we, if we look for this, we might else find it, but we could see that we are calling something called printf, which is our print function. Where is the, but we get the general idea that this is still human readable, but as you can see, it's a little bit hard to read because it's written, it's codified, and it's written in order to efficiently or have as much as letters or as less code possible. So this is the compilation step. You can see that, as I said, this file main.s contains low-level assembly instructions. For example, we could, like I said, you could see here that we are moving 68 into a register, we are moving 1 into a register, we are calling a certain subroutine, we are doing something here too, we are doing a bunch of instructions, we are returning. So, but you can, for example, notice that we have a subroutine here called main, and we have here another subroutine that is we call here, which is this. So my best guess is that this call to this subroutine is our function. So why did our function change the name? I don't know, but we could notice that this is the name of our function, which is called add. Because if I look in here, you could notice that we are calling something called add ln, and we are adding things that are in these two registers and putting it in here. So I would say that this is the subroutine that or the routine that matches our implementation of our function that adds two numbers. And this is our main program. So you can see that there is still a possibility, and the assembly language is still human readable. If you give it time, you can still read the assembly language because it's still readable. It's still you can still make sense of what is happening. So the next step is called the assembly. The assembler, as we saw in the last episode, converts the assembly code, what we have here, into object code, which is the machine-readable binary. So now we are starting to get into territories where humans start losing efficiency, or the fact that humans can read start to become a disadvantage because now we can't just read code that that a machine can read. A machine can read only binary numbers. So if a machine can read a certain file without translating it, it means that it's not readable to humans. So on this stage, on this compilation stage, we have produced a main.s file, which is the assembly code, and the assembly is going to produce a file that's called main.o. By the way, these names of files are arbitrary. You can give it whatever you want. So let's see how it works then. Sorry. So in order to produce a machine readable code, it's another command. So we give it we give it our we don't give it our we could honestly we could think I think we could give it our main.c, right? We could give it our main.c or main.s file. Let's see. So let's see if it's going to work. Main c main s, that's the right thing. So let's produce an executable called let's call it O in order to a little bit to to differentiate it from this main X, which is also an executable. So we hit enter and it worked. So let's read our object file. Let's take a look on how the object file produced looks like. As we predicted, we could see that it's obviously not human readable. Obvious, but there is certain things you could read, like you could read libc, start main. There's still some readable characteristics to it. I could, I could. There's a bunch of libraries that our program uses. For example, we use a dynamic library called the lib64. We use libc also. It's still readable, but there is no much information into this. So the next step is called linking. So the linker, which is also a program, by the way, all of these form a big program which has small programs. So here, the step number 5 is called linking. So, and the program that ensures the linking stage is called the linker. So the linker combines multiple object files, like main.o just produced on this stage. For example, math utilities.o, and links in external libraries like iostream or stdio.io, creating a final executable. So the main task of this stage is to connect the main function in the main.o to add resolve symbol from the standard library. So let's we could try to do it, but for now let's try to see if our main.o executable can be run. Yes, from now at this stage we already have an executable, a program that works. We already have a program that works because the linking has been already done. Either it works on this stage, or it works on this stage because probably we have already done the linking, or we are using libraries that are already defined in our program. We are not using too much of other libraries, for example. And the last step is when we have our executable like this. You can notice that our executable, there is the executable we made before. Going through this step, it gives the same number. So we just produced the same program, the same executable, the same program that give the same answers, but using different methods, which means that it's the same program actually. So this is a broad overview of what compilation is. Obviously, there is a lot of theoretical knowledge behind this, but this is the general idea of how programs like written in C or C++ are produced. Knowing how compilers work, linkers work, assemblers works, it's another topic for another video. And it's entirely another domain of knowledge. But what interests us and what interests this video is to see the general ways of how programs or compilers or compilation is done. Thank you.